Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topics is algorithms. So, today we will be seeing applications of binary search. In the last lecture we had seen the definition of binary search and why is binary search useful. Today we will be seeing more of binary search, try to understand it better, and then we will see an application of binary search. We will be using binary search to count the number of occurrences of an element in a set. To start with, what was the binary search all about? It was about searching of an element. So, we have been given a set S and we want to search if a given element x is in the set S. Now, one obvious way of doing it is to do an exhaustive search. What is an exhaustive search? You go over all the elements in the set S one by one and you check if if x is equal to any of these elements, and if you find one that is equal to x, then you can answer that yes, x is there and you can extract that element out, and otherwise you say that the x does not exist there. Now, this algorithm of course works, and in fact this is the best one can hope for doing in general. For example, we know that when we have a cupboard full of clothes or a bookshelves full of books kept in a randomly ordered way, and we are looking for a particular book or a particular cloth in the case of the cupboard, we have to go over all the books before we can completely sure that the book exists in the bookshelf or the cloth exists in the cupboard. So, exhaustive search in some sense the best one can hope for logically. But can we do something better when this set is a bit more structured? For example, if the bookshelf is ordered in the alphabetical order of the author's name, like it is done in the case of libraries, is it easier to search a book then? Or if we are given a list of names in a table, is it easy to search whether a particular given name exists in the table when the names are sorted in the ascending order of the names, and so on and so forth. There are many examples of structured sets we encounter in our real life and also in computers. So, of course, it depends upon what is the structure of this set. For example, if I just say that my cupboard has been ordered in according to colors, say all the red clothes are in one place and blue clothes in some other place, and then if I am looking for a piece of cloth that is made of silk or say, and I have no idea what the color of that cloth is, then looking for that piece of cloth in this cupboard which is sorted according to colors does not help. It is a natural understanding of this real life situation. But when this data set is structured in a particular way, then we might be able to do something better. And that is when that is what happens when we look at sorted list. Now, this is a typical example of a very well structured set. We have a set S which has n elements S 1 to S n, and this S 1 to S n is given in a way that it is sorted, means. So, we are talking about numbers, say. So, S 1 to S n are integers, for example, and this ordering is that S i is always less than or equal to S i plus 1, that is sorted in an ascending order. And we have been given this element x, and we want to check if x belongs to this set S. Now, this is where binary search come in handy. Of course, exhaustive search will again do the job, but it would require x, it will require us to compare x with x 1, then S 2, then S 3, then S n, all the n elements. So, exhaustive search will require n comparisons, whereas in binary search, using binary search we can do some slightly better. Let us say, for example, we have the set S 1 S, which is a set of integers 1, 1, 2, 3, 5, 8, 10. Note that the set does not need to be have the property that an element occurs only once. For example, here 1 occurs twice, that is completely fine, right. For example, when the books are sorted in the library, of course, there can be multiple books by the same author's name, and say we want to check if S is 7 is in the set S. Now, this is an example we saw in the last lecture also, but I would like to do it again. The main reason is binary search is something so important and so basic to the field of algorithms, that understanding every integrate details of this particular algorithm is very crucial for understanding of more complicated algorithms. So, we will go over this binary search algorithm once again. So, we have to check if 7 is in the set S. So, how do we start? We start with keeping two registers L and U. Now, for the sake of our purpose, L is the basically will indicate the index which is the lower index. It is like anything between L and U, anything whose index is between L and U can be a possible place where x belong, or in our case 7 belongs, and U in our case of course is 1, 2, 3, 4, 5, 6, 7, it is 7. It is the index of the last element of this set. To differentiate L from U, I will just make U to have these 2 dashes on top. Now, when we have L and U, so basically if 7 exists in S, then 7 must be in one of the elements between these 2 arrows. Then we will go to the middle arrow, which is L plus U by 2, which is the middle place, and then we will search for that place. So, let us see. To start with, what is L? L is 1, as I told, because it is not the value 1, but the index 1, and U is the index of the last element, which is 7 in this case. So, L plus U by 2 is 4. Thus, we will be measuring the fourth element, which is in our case this number 3 that has been marked in red. So, what do? We ask if 7 is less than S 4, and in this case the answer is no. If the answer is no, what do we know? We know that 7 must be greater than or equal to S 4. Thus, anything less than S 4, thus S 1, S 2, S 3 is not a valid candidate for 7. So, we can literally strike off the first 3 things, which is S1, S2, S3, and then we will move this pointer to here. So, we can erase this thing out and we will move L to this place, which is in our case 4. So, we update L to 4, U remains 10, and now we have a new M that we get, which is in middle of these 2 things, U and L and U, which is 6. So, which is 6, 1, 2, 3, 4, 5, 6. So, 6 is the number 8 in our case, and we compare, is 7 less than S6? The answer is yes, 7 is strictly less than S6. What does it mean? It means that if 7 exists, it cannot be S6 or S7. Thus, we can safely erase anything greater than or equal to S6. Here we are crucially using the fact that this set is sort ordered. Thus, the S7 is strictly greater than S6 and S6 is strictly greater than 7. Thus, we can erase that, and thus we will update our thing to 6 minus 1, which is 5. Right? We bring our U to here by removing this set, and we again do the same thing. We will next ask for the 5th place, and we keep on repeating this whole process till we have the L and U coming to the same amount, which is both 5. In that case, what we know is that all we need to measure when both of them becomes 5 is 7 equals to S5. So, this is the crucial part of the binary search, that we are halving our possible set of options by half every time. Every time we are having L and U, we are either making L to come to the middle or U to come to the middle, and we are halving the possible set of options. So, in the case of the binary search, which is given a set of n elements, and we want to check if x is in this n elements when the set of n elements is sorted, the pseudocode for that is this following. We have seen it in the last lecture also, and it is exactly same what we did. We initialize L and U. L is initialized to 1 and U is initialized to n, because that is the initially the all possible set of answers that can where the element x can be. And as long as L is strictly less than U, we keep on going to the middle point, which is L plus U by 2. If S is strictly less than Sm, then we can update U to be m minus 1, because we know that x cannot be Sm or Sm plus 1 or Sm plus 2 or anything above Sm. Else x is greater than or equal to Sm. Thus, we can remove Sm minus 1 and Sm minus 2 and so on. So, L is equals to m, and when L becomes equals to U, then all we have left with this one element Su or Sl, which is both the same now, and then we can just check if x is equal to U. So, this is the pseudocode of the binary search, and one of the main things to check is the termination of this algorithm. It is a bit crucial thing to check. It happens when, of course, when L becomes greater than or equal to U, this while loop stops, and the while loop stops because if L is strictly less than U, then one thing to note is that the way m is chosen, L is strictly less than m is lesser than or equal to U. Thus, at any point of time, either L becomes m, thus we will make a progress, L will go up by 1, or U becomes m minus 1, then m will come down, U will come down by 1. So, either L goes up by 1 or U come down by 1, and thus it will stop after n steps at least. This is where it is crucial that I have been using this ceiling part for m, and thus we have this strictly less than here. If you do not have the ceil and the floor, we will have the opposite thing here. So, we will take a break here and we will come back after the break to see more about this algorithm. Welcome back after the break. Before the break, we were looking at the binary search algorithm, and we saw the pseudocode of this algorithm, and we proved that this algorithm terminates. Now, to summarize binary search, the binary search correctly checks if a certain element is in a sorted list of n elements. It is crucial that it is a sorted list and not just any randomly ordered list. The number of comparisons made is log n plus 1. This is something we did it in the last lecture. The main idea is that, as I told, every time we are halving the u minus L distance, because every time either L goes to m or u comes to m minus 1, thus we are halving this distance every time. And so, after log n steps, this algorithm will stop, and in every round of this while loop we make only one comparison. So, it is log n plus 1 step, and the space complexity is constant, because all we are using is to maintain L and u. Now, binary search has some very important characteristics. The first option, which I have kind of skipped throughout my talk today and in the last lecture also, is that we were saying that L be 4 and u be 7 and u plus L by 2 is 6, and then let us go to S6 and check. Now, that going to S6, we are assuming it takes only one step, whereas in the case of a not a very well structured object, say if I give you a list of elements and say that, oh, can you give me the 14th element of this list? Of course, the most obvious way is to count one by one, 1, 2, first, second, third, fourth, and then you go to the 14th element. But sometimes in computers, if it is given in an array, as you know, we can just say that give me the 14th element, and it will give me the 14th element in just one move. This is what we call as a random access memory. Binary search is useful only for random access memory, because else for every time you ask that what is the S6 compared with S6, just to extract the element S6, we would have required at least 6 steps. So, that is not good. So, binary search does require the memory to be given as a random access memory. If it is given in some other form, for example, linked list, where random access cannot be done, then binary search does not give an advantage at all. In fact, if you do the calculations, it will come out that binary search is worse than exhaustive search. It can only work in structured data. So, we have here exhaustive search, which can work on anything, whereas in the case of binary search, it can work only for structured data. The big advantage why we keep on talking about binary search is that the number of comparisons is only log the size of the input of the list, whereas in exhaustive search it is linear in size of the list. This can make a lot of difference. When the size of list size is huge, say something like 1,000,000, then exhaustive search will take 1,000,000 steps, whereas the binary search will take only 15 steps, and it will come down to the main thing, because it is a log of the million, whatever it comes to, which is very small compared to the exhaustive search. So, a comparison of exhaustive search always works. It can work on any kind of data structures, but the number of comparisons required is linear in the size of the set. Binary search only works for sorted sets, only for random access memory, but when it does work, it works in logarithm the size of the set. This is the advantage of binary search. Now we move on to some other problem which are similar to what we have studied, and where we see the power of binary search or application of binary search. Say I have a set S which is S1 to Sn, and I have been given as element x, and now I don't just want to find whether x belongs to this set, but I want to count the number of occurrences of x in this set. How can I do it? Again, exhaustive check will do it, right? We go one by one over all the elements in this set. We ask, is S1 equals to x, is S2 equals to x, is S3 equals to x, and we keep on doing for n steps, and finally we keep a counter of every time we find some element is equals to x, we increase the counter, and after n comparisons we will give the right answer, which is the number of element times x occurs in this set. The total number of comparisons again will be n, because n is, you have to go through all the n elements in this set. Now, how can one use the binary search? The main idea here is that I first want to find the smallest I. So, note that the set is ordered. So, S1 is less than S2 is less than S3 to less than Sn. So, I want to find the smallest I such that Si is equals to x, and I also want to find the largest j such that Sj is equals to x. So, what do I know? Any element between I and j, so Si and Sj is equals to x, and nothing else is equals to x, because if something else is equals to x, then that would have, then j would have been equal to that element, or I would have been equal to that index. And finally, we have to count the number of occurrences of x in this set. So, that is j minus I plus 1. It is like if s equals to 1 and j equals to 5, it means that S1, S2, S3, S4, S5 is equals to x. So, how many occurrences of x exist? Is 5 minus 1 is 4 plus 1 5. So, now all we have to do is find the smallest I and largest j. And how do we do it? So, let us consider this new algorithm we call the finding the largest, and this find the largest j such that Sj equals to x, and here is the pseudocode of it. If you guys remember, this pseudocode is exactly the same pseudocode as the binary search pseudocode. It has been not been changed even at a single place. Why will it work? Binary search will of course output some index which is equal to x, that is clear, but why will this one output the largest index that will equals to x? And thus we have to look at the correctness of this algorithm, and the correctness of the algorithm is not very hard. Let us I be the largest index which basically this algorithm needs to output. Clearly, I want to prove that at any point in this algorithm or in this while loop, L is less than equal to I is less than equal to u. Why will it work? If it works, if this happens, then when this algorithm stops, the algorithm will stop only when L will become equals to u, or it will not find it, that is a separate case. But if it finds it, if x does exist in this set, then it will stop when L is equals to u, and then it will output of course I, which is what we want to output. And then the next question is, why is this particular equation holds? It equation holds is simple. You have to check for each of the cases. For example, let us look at this first one. If x is less than Sm, then x cannot be Sm. Thus, if I strictly less than m, and we have update u to m minus 1. So, if this if clause works, then I will be less than u. Again here, if the else clause kicks in, that means x is greater than or equal to S L. Since I am wanting the largest index, so I must be greater than or equals to m. So, thus we can see that this inequality is invariant in this whole pseudocode. So, this gives us the correctness of this algorithm. Now, how many comparisons do we need? Again, it is, since it is exactly similar to binary search, the number of comparisons will also be log n plus 1. Here is the pseudocode. I will not go into details of this pseudocode. Rather, I would just leave it as an exercise. All I had to do was change the ceiling to the floor and change these inequalities and accordingly make these correct changes. I would leave it for you guys to verify that this algorithm does find the smallest index. And now, when we have done, what we will do, our final output for algorithm for counting it is, we first run the finding the largest algorithm. If that outputs not there, that means this x is not even there in this set, and then we output 0. Else we know this x is there, and thus finding the largest will output the largest index which is equal to j. Finding smallest will output the largest index that will be equal to j, and then I will output the finding largest minus finding smallest plus 1. Clearly, this will give me the right answer. So, this will output the number of occurrences of an element in the set of n elements. The total number of comparisons that this algorithm will require is twice log n plus 2, with log n plus 1 for finding the largest and log n plus 1 for finding the smallest, and compare it with the exhaustive search. Exhaustive search kind of algorithm would have taken n steps. So, we are significantly better. Again, here I want to repeat that this algorithm will only work when the set is sorted and the set is given in a random access memory like a list. Now comes a very interesting question: can one do better than binary search, the algorithm that I just pointed out for counting the number of occurrences of x in a set? We know that the number of comparisons that this algorithm does is twice log n plus 2. Now, let us see what is the amount of information that we get for each comparison. So, every comparison will say that either x is equal to s I or something or not, or s I is less than equal to this or not. Every comparison just gives us one bit of information. Now, how many bits of information are required to be output? Note that when the number that we need to output is the number of occurrences of x in this set, that can be any number between 1 and n. A priori, we have no idea about how many numbers, how many occurrences of x is there in this set. It can be 0, 1, 2, anything up to n. So, in some sense you can think that we have to output a number whose length is log n, and initially we have no idea about the number bits in this output. So, we have to get log n bits of information, and each comparisons will give us one bit of information. So, this kind of says that this algorithm is optimal. We have a factor of 2 there, but other than that it is almost as good as one can hope for. To summarize, binary search for finding an element in a set, we have looked at it, we have studied it, we have tried to understand it, and then we again looked for some applications of a binary search for counting the number of occurrences of an element in a set. So, we will stop here. When we come back next time, we will talk about more applications of binary search. Thank you.